NMR spectroscopy utilizes the magnetic property of the carbon-13 and proton nuclei to determine the exact arrangements of carbon atoms and hydrogen atoms in the unknown organic compound of our interest.
Wow, it must be quite a powerful and expensive tool then.
It is. It's actually a new concept, so it's a lot to process at first. So let's take it slow and try to understand the main principle of NMR spectroscopy.
Alright.
Now, as the name suggests, NMR spectroscopy takes advantage of the nuclear magnetic property of carbon-13 and proton nuclei. Thus, there are mainly two types of NMR spectroscopy: carbon-13 NMR spectroscopy and proton NMR spectroscopy. Both share the same principle of NMR spectroscopy and are carried out by the same instrument.
So I'd guess that the carbon-13 NMR spectroscopy provides information about carbon atoms in a molecule, while proton NMR spectroscopy provides information about the hydrogen atoms in a molecule.
That's right. Now let me ask you a simple question. What would happen if you twist the needle of a magnetic compass with your finger so that the point facing the North Pole of the Earth faces the South Pole instead?
The needle will try to return to its original position. In fact, as soon as I let go of the needle, it will return to its previous alignment.
Correct. That's because the needle is constantly under the influence of the Earth's magnetic field.
Yeah, that's why when it's allowed to freely rotate, the North Pole of the needle will always point to the Earth's magnetic South Pole, which is actually the Earth's geographical North Pole.
That's right. Similarly, when a carbon-13 or proton nuclei is subjected to an external magnetic field, the nucleus aligns with or against the field.
I see. So the nucleus kind of behaves like the needle of a magnetic compass. But its alignment against the field must be unstable, right?
Yup. In fact, a nucleus aligned against the external field is at a higher energy state than one aligned with the external field.
So a stable nucleus will only go to the higher energy state where it is aligned opposed to the external magnetic field, when it's supplied with a sufficient amount of energy.
Yes, and the energy needed to flip the nucleus usually falls in the range of energies found in radio waves.
So I guess NMR spectroscopy uses magnetic fields and radio waves to analyze organic compounds.
Exactly, and when the nuclei interact with the radio waves of just the right frequency, it flips from one orientation to the other, which is then detected as a peak on the graph. This flipping of the nucleus from one magnetic alignment to the other by the radio waves is known as the resonance condition.
So that's why it's called nuclear magnetic resonance. It all makes sense now.
Indeed. And since this is also a spectroscopic method, the graph obtained is a spectrum.
Okay. Will we be using this instrument in our labs? I think if we have some hands-on experience, it'll be easier for us to understand.
Unfortunately, we do not have one in our school. These instruments are usually only found in universities and research institutes. Also, the practical aspects for NMR will not be tested in the exams. We'll only be learning about the theoretical aspects of it.
Okay.
But worry not. We might have a field trip to one of the local universities to learn more about it in the future.
That will be so cool. Speaking of these complex instruments, in the past, we learned about the mass spectra, which is a graph of the mass to charge ratio versus the relative intensity. We have also learned about the infrared spectra, which is a graph of the wave number versus the transmittance. So, what's the deal with NMR spectra?
Well, it's a little bit complicated. The spectra obtained in this case are typically a series of peaks like this.
It doesn't look that complicated.
Well, the thing is, the peaks are displayed on a scale of chemical shift values written as delta, measured in parts per million.
Now this sounds quite complicated.
Thankfully, we don't have to delve further into the units involved in this level. However, a simple understanding of the chemical shift is a necessity.
So, what is a chemical shift?
Well, before we discuss it, it's important for you to know what information can be derived from the spectra of a sample obtained from each type of NMR spectroscopy. So, let's start with carbon-13 NMR spectroscopy.
Alright,
The main function of this spectroscopy is to give information about carbon atoms in molecules. Thus, the technique utilizes the magnetic property of carbon-13 isotopes to flip.
right. That's what I thought. But teacher, what about carbon-12 atoms? Isn't this isotope in a majority compared to carbon-13 isotope?
Well, you must have realized by now that carbon-12 and carbon-14 nuclei don't have net nuclear spin, since they have even numbers of protons and even numbers of neutrons. However, about 1% of the carbon atoms in any sample of an organic compound are carbon-13 isotopes.
Now I remember. 99% of all the naturally occurring carbon are carbon-12, while about 1% are carbon-13. So, the peaks obtained in the carbon-13 NMR spectra are all due to the interaction of this 1% of carbon-13 nuclei with the external magnetic field and radio waves.
Correct. Therefore, the instrument for its detection needs to be highly sensitive.
Yeah, that makes sense. So what exact information can we get from the carbon-13 NMR spectrum?
There are two main things that you should look out for in a carbon-13 NMR spectra: the number of peaks and their chemical shift values in the horizontal axis.
Noted. Do the number of peaks denote the number of carbon atoms present in the sample of an organic compound?
Well, that's not always the case, but in some cases that might be true. Let me show you. For example, the spectra for 1 bromopropane will show 3 peaks. However, the spectra of 2 bromopropane only shows 2 peaks.
Interesting. It seems to me like each peak is for carbon atoms with different chemical environments.
You're right. As you can observe from the structural formula of 1 bromopropane, each carbon atom has a different chemical environment. 1 carbon is bonded to 1 bromine, 1 carbon and 2 hydrogen atoms. Another carbon is bonded to 2 carbon atoms and 2 hydrogen atoms. And the last carbon is bonded to 1 carbon atom and 3 hydrogen atoms.
It's visible that these carbons have different chemical environments. But how does this relate to the peaks in the spectrum?
Carbon-13 nuclei with different chemical environments experience the external magnetic field at different levels. So, different environments affect the resonance condition of the carbon-13 nucleus to different extents. That's why peaks are obtained at different chemical shift values.
I see. So that's why, in the case of 1 bromopropane, there are 3 peaks in its spectra. But in the case of 2 bromopropane, 1 carbon atom is bonded to 1 bromine, 2 carbon and 1 hydrogen atoms, while the other 2 carbon atoms are both bonded to 1 carbon atom and 3 hydrogen atoms. Since the 2 carbon atoms at the terminal of the compound are surrounded by exactly the same chemical environments, they have the same chemical shift value in its spectrum.
Correct. And atoms having the same chemical environment, like these, are said to be chemically equivalent atoms. And those that don't have the same chemical environment are referred to as non-equivalent atoms.
Got it. So the number of peaks in the carbon-13 NMR spectroscopy actually indicates the number of carbon environments present in an organic compound.
Indeed. This way, a carbon-13 NMR spectroscopy helps to deduce the arrangement of carbon atoms in an unknown organic compound and hence its exact structure.
Right. The 2 isomers of propyl bromide have different spectra, so we can distinguish which one is present in a sample simply from the carbon-13 NMR spectra.
Yes. Similarly, you can distinguish between a pentane 2-one and a pentane 3-one by looking at the number of peaks in their spectra. Do you think you can explain how?
I can try. For that, I'll have to start by writing down the structural formula of pentane 2-one and pentan-3-one. Pentan-2-one has 5 carbon environments, so it will show 5 peaks in the spectrum, while pentan-3-one has 3 carbon environments, so its spectra will show 3 peaks.
Finding this helpful? We have additional learning resources to offer. For Cambridge IGCSE and AS A-level subjects.
Indeed. So let's try figuring out the isomer of a molecule by looking at another carbon-13 NMR spectrum.
Alright,
Can you identify the isomers of an aldehyde with the molecular formula C4H8O with this carbon-13 NMR spectrum?
I remember that there are 2 isomers of C4H8O that are aldehydes, butanol and 2-methylpropanol. All 4 of butanol's carbon atoms have a different chemical environment, so they'll give 4 peaks in the spectrum. In contrast, 2 of the 2-methylpropanol's 4 carbon atoms have the same chemical environment, so it will give 3 peaks in the spectrum. So obviously, the spectrum given here is that of 2-methylpropanol.
Correct. You really got the hang of this, Divash. I think you could even try working out the isomers of aromatic compounds now.
I think I can. Won't a benzene molecule only have a single peak in its carbon-13 NMR spectrum despite having 6 carbons?
Indeed, and that's because all 6 carbon atoms have identical carbon environments. However, if we substitute even one of the hydrogen atoms of a benzene molecule with a different species, the number of peaks will increase.
Oh yeah, a methylbenzene will have 5 carbon environments and hence its spectrum will show 5 peaks.
Correct again.
That's crazy. A single substitution has such a huge effect on the carbon environment.
Indeed, in turn, it also affects the chemical shift values of the carbon present in the molecule. So the peak of the carbon will appear at 5 different chemical shift values. Take a look.
Right. Teacher, now that we know all this, I really think we've waited long enough to learn about chemical shifts, haven't we?
Alright, since you've done so well in this lesson, you deserve to know about it. But at this level, you'll only have to understand chemical shifts at a surface level.
I don't mind. That's even more convenient for me.
Great. Well, now, as you can see in a carbon NMR spectrum, the scale starts out with a 0 point at the far right. This 0 point is where you would find a peak due to carbon-13 atoms in tetramethylsilane, which is also written as TMS. The position of all the other peaks is measured as a shift from this 0 point, which is called the chemical shift.
So TMS serves as a reference for the carbon-13 atoms of other organic compounds.
Yes.
But why specifically TMS?
That's because, first of all, the molecule contains 4 methyl groups attached to a silicon atom in a tetrahedral arrangement. Thus, all the carbon atoms in this molecule are chemically equivalent.
So they will form a single peak. Right, I get that. But there are other compounds that also give a single peak, like benzene for example. Why is TMS so special?
That's because only TMS can give a strong peak at the extreme right of the scale, much more so than any other compound, which ensures that its peak won't obscure the peaks of the compounds that we want to identify.
I guess this has something to do with the carbon-silicon bond.
Indeed, but we don't have to delve further into that topic at this level.
Great, then I won't pry any further. However, I do want to know if there are certain values of the chemical shift for certain chemical environments.
Well, instead of exact chemical shift values, we have a list of chemical shift ranges for carbon-13 atoms with different chemical environments. Take a look.
The position of a peak isn't just affected by the type of atoms attached to it and its hybridization state, but also the type of atoms attached to the adjacent atoms.
Yes, this is because different neighboring atoms have different effects on the resonance condition of carbon-13 atoms.
Got it.
Want to learn more? We have additional learning resources to offer for Cambridge IGCSE and AS A level subjects. Register now for free.